superposition of two harmonic waves having same frequency, amplitude, and propagating in same direction, but differing by a phase difference phi. Let's see now. So we have two waves and both of them are superimposing on each other, but both of them have a phase difference of phi. So let's assume our first wave is y1 xt, and that is equals to amplitude A sine kx minus omega t. This is our first wave, and the second wave has an amplitude same as the previous one. Everything is same, k is same, x is same, minus omega t, only there is an extra phase difference phi. Now if such two waves superimpose on each other, then according to superposition principle, y will be equals to, y is the resultant wave function, let me write, it is also a function of x and t. It will be the sum of y1 xt plus y2 xt. We know that the superposition principle says that the total wave function of the resultant wave will be the sum of individual wave functions of first and second wave. So y1 xt plus y2 xt. Now what we will do, we will substitute the value of y1. y1 is A sine kx minus omega t plus A sine kx minus omega t plus phi. Now let's take A common out and we left with sine kx minus omega t plus sine kx minus omega t plus phi. Now we have sine A plus sine B. So we will use a mathematical formula from trigonometry, sine A plus sine B. Sine A plus sine B, it gives us 2 sine A plus B by 2 from trigonometry, cos A minus B by 2. This is the identity we will use here. Using this identity over here, A here is nothing but kx plus omega t and B is kx minus omega t plus phi. Let's substitute this, it will be A, and we left with 2 times sine kx minus omega t plus kx minus omega t plus phi whole divided by 2 into cos kx minus omega t minus kx minus omega t plus phi whole divided by 2. Next is, let's simplify this. So this will give us twice of A sine kx plus kx, 2kx minus 2 omega t plus phi whole divided by 2, and the second parameter is cos kx minus omega t minus kx plus omega t minus phi whole divided by 2. Let's simplify it further. So it will give us 2a sine 2 and 2 cancels, you left with kx minus 2 omega t upon 2, omega t plus phi upon 2, cos kx cancels with kx, omega t cancels with omega t, we left with minus phi by 2. Now, if I take this cos minus phi by 2 in front, it will be 2a cos, and cos minus theta is from maths, plus theta. So cos phi by 2, and here you left with sin kx minus omega t plus phi by 2. This is our resultant wave function of two harmonic waves having a phase difference phi. Now this is very important to know that this part is known as the amplitude of the resultant wave. Why? Let's see. Let's go to the previous lecture. If the phase difference between the two waves is 0, then from here this equation yxt will be 2a sin kx minus omega t. The same thing what we got in the previous lecture. But if the phase difference is pi, if the phase difference is pi, cos phi by 2 will be cos pi by 2, and that is nothing but 0. So that places the amplitude will get cancelled and the resultant will be 0. And when does this happens? Let's draw this. This I have already drawn. Let me draw it again. The first scenario, the red one. In this case, you have one wave and another wave. Both the waves are, let me draw it 1 second. So this will be first wave, and let's say this is a second wave with the crest falling on the crest and the trough falling on the trough. When this thing happens, the resultant will be doubled. The amplitude of the resultant wave will be doubled the initial wave. But in case of the second part where phase difference is pi, in that case what happens? If this is first wave and the second wave will be the crest is falling on the trough, so they both will cancel each other and there will be no wave at that point. Y will be 0. So this is your resultant of two harmonic waves having phase difference phi.